Hello everyone. Today I'm going to summarize the clarified practical takeaways from the new paper, Scaling Laws for Precision. The paper gives us some intuitions and takeaways on how we should approach training and post-training quantization. First, the initial takeaways are not directly related to quantization. So they told us what are the overload bottlenecks of LLMs. Then what are overload bottlenecks first? During training or inferencing LLMs, some tasks can be done concurrently, like moving data and performing compute. Compute here refers to the arithmetic operations. So the overload bottleneck means that we are waiting on before we can proceed to the next step. And the bottleneck could either be moving data or performing compute. This paper tells us that during training an LLM, compute is the major bottleneck. Essentially, everything is waiting for a matrix multiplication results. And the data is already prepared for the compute. And during inference, it's more about memory bandwidth being the overload bottleneck. That is, the data movement between different parts of the GPU. And it's usually not moving data from CPU memory to GPU memory, assuming you have programmed it properly. And for two specific scenarios, for small batch inference, the memory bandwidth is mainly bounded by moving model weights. And for long sequence decoding, it's more bounded by moving the KV cache. Now we need some definitions. Quantization can be done during training, and the objects to quantize are weights, activations, and KV cache. Usually, KV cache is considered part of activations, but here they separate them. The activations are the output of layers, excluding the KV cache. And quantization can be classified as quantization-aware training, which only quantizes the weights without affecting activations and KV cache. This kind of quantization doesn't save compute during training. That's because from matrix multiplications, you still need to convert the quantized weights back to the original precision, like bfloat 16. And the purpose is to adapt the quantization for inference. Specifically, if you train the model to be robust to less precise parameters, during inference, you don't need to worry about the loss of precision on the same model weights. And low precision training is when we quantize weights, activations, and the KV cache during training. So this saves compute during training because the matrix multiplications are done with the quantized variables. And the quantization during inference is also called post-training quantization. That is, the objects to quantize are the weights. The quantization approach studied in this paper is GPTQ. So it has a calibration process, which means it changes the model weight values as they are being quantized to minimize the loss of precision. And this is different from GGUF. Now let's talk about the post-training quantization scenario first. So the models are trained in bfloat 16 and then quantized with GPTQ at different precisions. And the evaluation metric is the degradation of validation loss after quantization. One takeaway here is that for models of the same size, when it is trained with more data, degradation in validation loss will grow. In this figure, the model has 30 million parameters, and the x-axis shows the token-to-parameter ratio. From left to right side, more tokens are used to train the model, and the y-axis is the validation loss. As you can see, the degradation is larger as the model is trained on more tokens. And for the case of quantization to integers of 3 bits, with more training data, the validation loss even grows. That means when you train the model with more data and quantize it to 3 bits per weight, the model will perform worse than the model trained with less data and quantized to the same degree. So this is out of our expectation. And another takeaway is that for the model trained on the same amount of data, if the model is larger, the degradation is smaller. That means when the model is less overtrained, the degradation of validation is smaller from the quantization. So from the 2 points, we can conclude that overtrained models are more prone to quantization. Now let's talk about quantized training. First, let's discuss quantization-aware training, where we only quantize the weights. Here, we need to understand the concept of effective parameter count. The effective parameter count depends on the bit precision of the parameters and the number of parameters. According to the paper, bit precision and parameter count interchangeably contribute to the model's effective parameter count. So here is my explanation. For a model with n parameters, and each parameter is represented with p bits, so the precision is p, and the effective parameter count is n times p. You can think of it as the total number of bits to represent the model. The takeaway is that the bit precision of the weights can be traded off for the number of parameters. That means the validation loss of a model with more parameters and lower precision can be the same as the loss of a model with fewer parameters and higher precision. However, this trade-off stops when the precision saturates, which is around 6 or 7 bits per weight. When the precision reaches 6 or 7 bits, if you increase the bits per weight further and reduce the number of parameters, you can't get a model with the same validation loss. So that means the model will perform worse if you go that way further. Regarding low precision training, when we quantize weights, activations, and the KV cache, the first takeaway is that the precision of activations and KV cache affects the validation loss in a similar way. So if you reduce the precision of activations and do it the same way, to the same degree for the KV cache, the degradation in validation loss will be similar. Here you can see an equation. So the effective parameter count depends on the precision of weights, activations, and KV cache in a similar manner, and they are independent of each other. Then, in the first training scenario, we fix the overall compute for the training and fix the training at the same low precision. So in this scenario, the takeaway is that to minimize the validation loss, you should increase parameters and decrease data. So this is pretty similar to the takeaway for post-training quantization. For models trained on the same amount of data, if the model is larger, the degradation is smaller. So here it's the same. If our quantization is the same with more parameters and less training data, the performance degradation is smaller. And another scenario is we only fix the compute, and we are free to choose the quantization, degree, and number of parameters and training data. So the takeaway we have is that the optimal precision used for training is around 7 bits. Using bfloat 16 is a waste of parameter precision, and 4 bits is not enough for the training. So it unnecessarily reduces the validation loss. And the next scenario is to fix only the parameter count, meaning the model size. Then the takeaway is that when you are training with more data, you should use higher precision. This is intuitively similar to the previous takeaways. And here is the last takeaway. They derived an equation to show the scaling law with consideration of quantization, or let's say precision. This equation can be referred to for planning out the training of an LLM. However, the fitted values of all coefficients and exponents can vary drastically based on small implementation differences. So this is discovery from previous papers and also cited in this paper. It means there are constants or coefficients like A, B, E, alpha, beta in this equation. The authors can provide the values they obtained, but the values may not apply to other model architecture, even though they are similar, or other settings. So while the equation remains informative, you shouldn't rely on the specific values for the coefficients. And that's all. Thank you all for watching.